Thank you all for attending today's NUG Community Call and training. Today's training is going to focus on power capping on Perlmutter. Myself, I'm Charles Lively. I'm a science engagement engineer and HPC consultant here at NERSC. I also have with me my counterpart and colleague, Lippy Gupta, as well as my colleague, Xingji Zhao. Lippy and Xingji, would you care to introduce yourself, tell everyone about your roles here at NERSC and anything you care to share?
Hi, welcome everyone. As Charles said, he and I work very closely together on these kinds of events. Though Charles did most of the work for this event in particular. We're always looking for good ideas, so feel free to reach out to us if you have a topic in mind that you haven't heard about recently, but would like us to put together some kind of presentation for, or any other kind of engagement activities that you think would benefit the community. We're happy to put those together. Thank you so much.
Yeah, hi everyone. I'm Zhengji Zhao from a different group than Charles and Lippy. So I used to work in the user engagement group, but a couple years ago I switched to advanced technologies group. So my current duty is to do power and energy analysis for our current and future systems. So we can continue to provide the users like increasing, enhanced, system performance. Yeah, that's my current role. Thank you for joining our today's training.
Awesome. Thank you both, Lippy and Xingji. So today we'll just dive into things. We'll start with just a general overview and discussion on the importance of power and energy efficiency, as well as introducing power capping on Perlmutter, which Xingji and the Advanced Technologies Group has led. And we'll follow that up with more case studies, as well as a few demos by Xingji as well. All right, and as we get going throughout the presentation, please, we encourage you to engage, interact, ask questions, so we can have just a productive and useful discussion. And so before we do get started, we just have a couple of few little icebreakers and questions to help lead and engage the conversation. So my first question, and you feel free to enter it in the chat, is how much of a supercomputer's total cost of operation do you think comes from electricity and cooling costs? If you want to just enter your thoughts into the chat. If you have a percentage-wise, like 15%, 30, 50, we're getting a couple of different variety of different answers, ranging from 15, 30, 45, 50%, 80, 70. And so a lot of industry data and estimates put the total cost of operation at about 40 to 50% for most global supercomputing centers. And even at NERSC, me and my lead, we were trying to figure out the total cost based off of our budget, and we were in the range of about 15 to 25% from what we were seeing. But that is a large cost of operation, and of course, if you're able to reduce that and optimize that cost, of course, that means that you can, you have more money to put into other activities and initiatives. So if you had to guess, how much of the world's electricity do you think data centers and HPC centers and AI data centers consume globally around the world? Put that estimate in a range of, do you think it's 1%, 5%, 10%? we got a couple of different answers. Anybody else want to take a stab at it? So we'll actually address this with more details in a few minutes. But the current estimates on average are in the range of 1 to 4% as of 2024. But that is definitely expected to grow with the emergence of AI data centers and AI training. So now we'll go into a high level overview of what we'll talk about. A little background about NERSC and the DOE's mission and why we believe power and energy consumption is so important, why we're concerned about it, and how can we understand how to implement power and energy consumption efficiency initiatives within our environments, as well as an intro to power capping on Perlmutter. And so again, NERSC, we're a DOE Office of Science Research facility, and we're basically a user facility. And our goal is to enable researchers like all of you to achieve your scientific goals and scientific initiatives. And we have researchers in various areas doing various simulations and great scientific studies, ranging from bioenergy and environmental simulations, nuclear physics, fusion energy, and materials and chemical simulations as well. And so we have over 10K users and various different projects as well. And so why do we want to focus on energy efficiency? Of course, it's going to be vital to the DOE for several reasons. The cost savings, of course, are important. It enables the DOE to reallocate costs from that expenditure to other grants and scientific endeavors as well. But also by reining in energy costs, we're able to do more complex simulations by minimizing the damage that can be done to our systems as energy consumption grows. And so throughout our work, our goal is to create a supporting and sustainable energy efficient environment. So we want to promote supercomputing capabilities, but by reducing our energy footprint as well. And so as we talked about previously, energy costs can account for a large percentage of total operating costs at HPC centers, on the range to 40 to 50%. And so that can, run up to several millions of dollars per year, right? On a global scale, data centers are estimated to consume about 1 to 3% of the world's electricity. And that's a significant contribution to carbon emissions as well. And so what we want to do is improve energy efficiency in order to provide for more sustainable approaches to computing. And again, if we have energy, it can be a limiting factor. So if we have a higher energy requirements, then that's going to make us need to implement more complex infrastructures to facilitate that. So energy efficiency is going to be is crucial moving forward for computing to continue to make strides as it's making. And so, this is a little kind of high level overview with various estimates on energy consumption around the world. Within the global data center share, we estimate between 1.5% to 3%. The actual US share of that global data load is approximately 45%. And we also have the AI and HPC share of that accounts for 15 to 24%. And data center global CO2 emissions from data centers and is in the range of 0.3 to 2%. And so those are 2024 estimates, but projections for 2023, we can see notable increases as well. with the data center share of global electricity going to top more in the higher range of greater than 3%, with increasingly growth throughout. And the CO2 emissions resulting by 2030 could triple as a result of the increase in computational workloads and various AI-based data centers as well. So does anyone have thoughts on why that might be such a big problem for the world, for users, for our environments, as well as for our achieving our scientific accomplishments? We got a couple of questions. And again, if we're not able to provide a direct response to your questions now, we'll have those in the Q&A document and we'll follow up directly with you as well. Okay, and so now let's just, let's recalibrate just a few specifics to help us understand. So when we talk about power consumption, we're talking about basically the voltage times the current. So V times I, and that's our typical formula for understanding power consumption. And energy consumption is simply just power consumption over time. So energy is going to be power times time. Power usage measured in watts, and time can be measured in, a basic calculation of seconds or hours or whatnot. And so that's just the essential measurement for us to understand power and energy consumption. And so again, power can be a limiting factor as it affects technology, or computing power constraints and GPU power constraints are limited based off of the power efficiency. So as clock speeds increase, power efficiency power consumption increases as well, and that can be a limiting factor. And so what we want to do is make sure that we are focusing on understanding and capitalizing on how we can minimize our power constraints so that we can have so that we can reduce the amount of power consumption on our hierarchical systems. And so with that, the end of Moore's law in a traditional sense, we're more towards focusing on how we can improve performance within our power limitations, which is why it's important for us to understand how we can implement power capping on Perlmutter. So trends that we want to keep in mind when dealing with power consumption, doubling performance per socket within power limits can be used to help improve our performance per socket efficiency. Industry is currently trying to look towards ways to boost that performance without that proportional increase in power consumption. And what we want to do is effectively manage power consumption for both socket levels so that we can have more power efficient computing technologies. And so we have, tighter CPU and GPU integration that allows for that as well as a rise in more power efficiency within storage mechanisms as well. And that's another factor to take into consideration, is that different components of the system utilize power as well. So it's not just the power that's being used by the CPU or the GPU, but there are also various other components that come into play. And so those components, it's the processor, it can be memory, it can be storage, as well as the cooling systems. Those all have very different and specific energy requirements. And so, Perlmutter at a high level, everyone's familiar with Perlmutter in our system. This diagram just shows you some of the basic interconnections, how you're able to access it through our SPIN gateways, the Ethernet and interconnect that we use for connecting to storage, as well as to other mechanisms as well as data transfer. And so looking at Perlmutter and understanding our power consumption and the components that are within it. So we have over 1,800 GPU accelerated nodes with each one having 1 Milan CPU and 4 NVIDIA A100 GPUs. And then we also have our CPU only nodes as well, over 3,072 containing 2 AMD Milan CPUs. And again, all connected with the Slingshot 11 interconnect with our Lustre file system as well. And so our thermal design power is the maximum amount of heat that a computer component can take. And so we have a breakdown of some of those different components that are listed here as well. And so what we want to understand moving forward is some of the different components that we can use to manage and optimize power consumption and energy efficiency on Perlmutter. All of these different components dissipate heat, and that requires us to have different mechanisms in place to cool the system, to maintain performance, and minimize any system outages. So at a high level, this is just giving you kind of like a under the hood view of how our nodes are constructed, or our GPU accelerated nodes, as well as our CPU only nodes as well. So all of these various components, as you're doing your simulations, they produce heat, and then we have various mechanisms in place that are required to dissipate that heat. And so our power usage effectiveness is in the range of 1.05 to 1.08. We use direct cooling mechanisms within our system as well. And then we have the Slingshot network, which has quadruples the GPU node bandwidth as well. So different ways we try to mitigate and minimize power consumption on Perlmutter. And so now, what is GPU power capping? And so GPU power capping is basically a feature that will allow for users to set a maximum power limit for GPUs during your job execution. And you can basically look at it like your budget. Everyone, when you are doing your simulations, you have your allocation, you have a number of hours that you can use. You can also kind of think of that as like, okay, how can you stay or within a power budget? Same way you stay within a allocation hourly budget as well. And so why use power capping? We want to use power capping because, of course, it's going to enhance energy efficiency. We want to reduce the thermal output and overheating of our components. And because that potential overheating is what leads to performance degradation in the hardware and system outages as well. And so Perlmutter has the capability now for users to define their power limits so that they can optimize their job performance as well as energy consumption. And so, again, the benefits of implementing power capping, we want to focus on energy efficiency to reduce those overall operational costs and environmental impact factors. Thermal management, again, optimal temperatures to help maintain and extend the lifespan of the hardware. And also energy efficiency leads to more performance stability because it's preventing power-induced throttling as well. And then also introducing power capping allows for an additional mechanism for resource allocation and scheduling within our Slurm scheduler as well for system utilization across multiple jobs. So we'll have more details later on how to implement power capping, but essentially what you want to do is we have a Slurm command that you can use for GPU power setting. And so in this example here, what we have is the GPU power is set to 200 watts. And so this will basically keep that power cap to 200 watts for your job. So the idea is that you want to choose a power cap that can balance performance with your energy efficiency goals. And so we'll get into more details about some of the available tools that you can utilize for managing power capping usage. You want to make sure you're monitoring your job scripts, ensuring that you have a desired power cap setting. And then you want to also analyze, your post-job performance for power usage and data access as well. And so this type of approach to it allows for us to understand the relationship between power settings and job performance, as well as it can assist in training to optimize your simulations for more efficient energy efficiency moving forward as well. So how can you apply power capping in your SLARM scripts and so basically, again, you want to implement the GPU power capping flag, set that to 200 or to approximate value. On Perlmutter, we have ranges of 100 watts to 400 watts on the 40 gigabyte GPU nodes and 100 watts to 500 watts on the larger memory nodes as well. And so we're going to get into a few case studies by Zhengji, but some best practices and considerations to keep in mind with power capping is, start with baseline measurements to establish your benchmarks and your current performance and power needs, and then gradually reduce power caps so that you're able to optimize that imbalanced performance and efficiency. And you want to keep an eye on key metrics again, completion times, utilization factors for the power consumption to really analyze the performance and power trade-off. And also, we encourage everyone to engage and share your thoughts in the NERSC user channel on what you're noticing with any power capping issues or power utilization as well, so that everyone's able to learn from everybody else's experiences. All right, and so with that now, what we'll do is segue into some detailed case studies. Zhengji, are you ready to continue with that?
Yes, so let me share my screen. Okay, so I hope I shared the right window. Do you see my, okay.
Yep, looks good.
Thank you, Charles, for the introduction of the, power capping and the importance of power and energy at NERSC and other data centers as well, and actually also globally. So next I will talk about some case studies we did in the last couple years to prepare for this more power constrained future, basically. So we have 1 second. Okay. So I would like to start with our workload analysis slides, which here shows the machine time breakdown by applications. So as you can see at NERSC, a few top codes, I think it's up about 6 or 7 codes, they account for about 50% of the total machine time on Perlmutter. So the motivation for us to look in depth the power behavior of these top applications here is to understand our workload's power behavior. And then the underlying motivation is when the power become further constrained, we want to use the application-aware power management so that we can achieve good, the better energy efficiency. We can run our systems under limited power. Meanwhile, we want ensure the application's performance. So you can consider when the power constraints is more rigorous, I mean more strict. One option is we just apply uniform power cap, so we stay within the power limit. But by doing that, we may cause some of the applications get a big performance hit, while some of them are not. So the application-aware power management trying to do more intelligent power allocations between the jobs so that we can stay within the power limit, but we want to make sure applications can run with the best possible performance. So this is the motivation for this work, and we have in these case studies, we're gonna cover these top 3 applications. If we sum up their percentage, it's about 34% of the NERSC workload. So the first one, VASP-based materials science code. The second one is Lattice QCD code. The third one is Earth system simulation code. And we want actually we evaluated the GPU version of it. So I believe the most of the workload for E3SM at NERSC still CPU focused, but this is the future, the future of this code. So we evaluated the GPU version of this called Scream. This is just for completeness, but because Charles has covered this page, so I just want to mention a couple things here. So in this study, we focused on the GPU nodes only. So as you know, this is for GPU power capping. So I want you to pay attention to this thermal design power for GPU. So our system, we have A100 GPU. So it's a TDP in simple. I mean, the thermal design power is 400 watt. And then for the GPU node, we estimated the node TDP is about 2400 watt. And then for the power measurement, we want to mention NERSC has the whole infrastructure that can monitor and collect the power usage data for all the jobs we run on the users run on the system. So it uses Cray power monitoring counters, and we also can use NVIDIA's DCGM to collect power data as well. So the sampling rate is about 2 seconds. So actually we collect data every second, but because some issues, it's a large amount of data, and during the aggregation, some data just get dropped in the data pipeline. So basically, we get 2 seconds sampling rate for power. With this, we can start the first application here. So I want to emphasize, so the benchmark selection is very important in any of the study. And basically for us, from the beginning, we think about the production deployment of our results. Let's say we investigate on, the understanding the power behavior and also their applications response to the power capping. Then we wanted to make sure this knowledge is enough or is to be used for production deployment. So we selected 7 benchmarks for VASP, which we think they are representative of our production VASP workloads. So we considered the many factors when selecting benchmark, but some of them large in size and some of them small. But for the purpose of this presentation, what we want to just categorize here is the first three benchmarks. They are so-called higher order method. So they are in general more compute and memory intensive, and the rest four is more basic computation in this code. So they relatively have lower compute and memory requirements. So I think first thing people would like to see is what is the power usage pattern looks like. So I listed here the only 3 out of 7, actually not 7 for each benchmark. We run many different runs at different node counts. So we have quite a lot of power pattern, but these are more kind of selected representative pattern. So as you can see, they are quite different. So if you look at the peak power from this, this is one of the higher order method. It is around 1500 watt area, but for this one, this is the basic DFT computation, and you can see there are much lower the peak power. And then in terms of pattern, this one shows periodic dips in the peak power, and this one is showing much more like irregular power use. So some portion of this method, this was still in work in progress, importing to the GPU. So there are some big portion here still was in CPU only. So you can see its power usage is lower. But regardless, the power usage difference, the common feature we can see is that the power usage is significantly below the node TDP here, marked in the pink magenta color here. And then the majority of the power, the dominant part of the power usage is provided by, is consumed by GPUs. So this is the GPUs, the 4 GPUs power usage. So in much of the study, we can see we focus on GPU's power usage. So now let's, because we want to catch the dynamic part of the power behavior, so for each benchmark, we run with different node counts to mimic the production usage of the application. So as you can see, the power usage varies significantly between different workloads. For example, this one is higher order methods, and the lower part, these are the DFT, the basic computations. The power usage is quite different. I forgot to say this is the power per node. So in all of our benchmarks, we focus on the average node power, because all the benchmarks selected so that each node do the similar things. So they should have the similar power usage. So we did here we show the average power per node. So you can see the power usage varies significantly with the workloads. And workloads here, we basically show the different methods we showed earlier. And then and if we look at the power change over concurrency, they relatively change slowly. So this is a nice feature. So when you look at to apply the power capping on the VASP workloads, probably you are less concerned about parallel concurrency. Probably you should pay more attention to the different the workload type. So now we want to apply GPU power capping, and we want to see what is the effect of power capping. So here I show here like two set of figures, one for 400 watt, which is the default on Perlmutter. So it's shown in blue. This is node power, and then the green is GPU power. And then another one is at 200 watt. We show in red. This is node power, and purple is for GPU power. So this is one of the benchmark we used. So you can see that the effect of GPU power capping is quite obvious. So the first, we can see that when applying this 200 watt GPU power cap, we see about 50% reduction in peak power usage. So we compare the blue, the tip of the blue line to the red one. This is about half of the power usage. So this is great. And we see about 10% slowdown, which is reasonable. By reasonable, we mean we just didn't provide enough power to meet the application's requirement. So the performance is naturally slowed down. And this slowdown we can see is roughly 10%. And in addition, we see that 60% decrease in power fluctuations. So fluctuations roughly you can measure from the peak to the bottom here, peak to trough, and this one is decreased by about 60%. So this is quite a nice feature because the large power fluctuations can have negative impact to the data center infrastructure as well as electricity grid. So this is a nice feature for us. So I didn't list other impact. For example, the lower GPU power cap can lower the operating temperature so that it reduces the cooling requirement and also extend the device's lifetime. And all these are positive side of this other than the slowdown here. So now let's look at the performance and the energy consumption when the power cap applied. So the first one shows the normalized performance of VASP, and the horizontal axis shows the power limit. So you can see that the VASP performance slowdown is, this is the default, and all lines, they are normalized over the 400 watt performance. So you can see that up to 10%, this is about 10%, performance slowdown is observed at 200 watt. So here I'm looking at 200 watt because this is an interesting area. So if you see the even lower power, at the even lower GPU power capping, you see the performance slowdown is quite large, more than 40%. So probably we want to use apply this type of power capping for the application, but 200 watt seems to be reasonable. And for some of the benchmarks, like these dots, actually we can apply further GPU power capping to to get more benefit in energy consumption. But this is something we see from here, up to 10% of performance slowdown. But if we look at the normalized GPU energy, so at the pink one, still the same benchmark, we see that the energy saving is about 18%. This is for GPU power capping. But if we look at the total energy, this is about 13 to 15% of total energy saving. So here we are just talking about up to this type of energy saving. But for these dots, if we tune it to further down to this part, we should be able to make all the application, all the benchmarks to achieve larger energy saving within reasonable performance hit. So we have a very detailed study in this paper, and it's available here. I put the URL there. So the second one, we can go a little bit faster. Basically, we did a similar thing. So this is the work by one of our summer student, Fatia Khan from Boston University. So he did the meso work for this milk analysis. So basically, he took the NERSC 10 benchmarks, which evaluate two of the workflow stage, generation and the spectrum in milk, and used four different input. This input just with a different lattice size, and then for each of the input size, he ran with three different parallel concurrency. So again, the purpose of doing this type of measurement, running different node counts, is to mimic the production workloads, and we want to see the dynamic feature of the power behavior. So this is the typical the power pattern, the power usage pattern. This is a node power over time. And we see a little bit, a quite different power usage pattern. So for generation, we see more periodic dips in the peak power, more visible, but for generation is more steady. But their power usage is around 1500 watt. I'm saying this without showing all the figures, but that's something we observed with many of the runs for milks. So I didn't mention in the VASP the data part, presentation part, but in our case, for all the applications, the power distribution is not normal, a normal distribution. That means they have multiple modes. For example, this is obviously 2, and all of them is at least 2 modes. So for best describe the power usage per node, we use the so-called high power mode. That's basically is the higher power range, usually corresponds to the core phase execution. So for that part, we use the high power mode. You can consider that as average of the higher power usage phase. So this is the power usage of, but here we show the GPU power usage for milk as shown earlier. So the GPU power is the dominant part in the node power consumption. So you can see the whole picture here. So for each different size of the benchmark, if you look at the GPU power usage, when the yeah, okay, there are more detailed description here. So we identified the lower part, they corresponding to the I/O, but the higher power part, here they are showing the regions for computation. And again, similar to VASP, the power usage don't reach the TDP here. Here we are comparing the GPU and the sorry, let me go back. Okay, sorry, I think I missed one point here. So basically we see a change, the power changing pattern here is when the concurrency increases. If we focus on simple benchmark, we see the power decrease. And we can see if one GPU change in 50 watt, 4 GPU is 100 per node. It's like we can see visible power change when increasing the concurrency. Okay, so now let's look at one power capping applied, how the energy and performance look like. So the left figure shows is the previous figure. We just show the result for the small benchmark. This is a generation application. So you can see that, and here this is the relative execution time, and here shows the energy. Here the energy is the GPU energy. So what we can see here is at up to 250 power cap, we didn't see any performance slowdown. Although you see the power usage, there are a big cut to the the node power usage here, but we don't see the significant performance slowdown. But if we look at the 150 watt, the power cap, we see significant performance slowdown. So again, 200 watt is the interesting area we may want to look into further. So at 200 watt, we see that the performance slowdown is about 10%. I think the 15% slowdown, we included Spectrum. Spectrum had a larger slowdown, but for generation, it's about 10% slowdown. But the energy saving is quite significant. It's about 28% reduction in energy consumption. It's not easy to see. We didn't show the relative energy use here, but this is about 28% of GPU energy. So for next case, it's a Scream. It's one of it's one of the it's should called resolution or simple cloud resolving E3SM atmosphere model. So this one is implemented in GPU. So again, when we choose the benchmarks, we try to select different input, different resolution here, and then we also run each benchmark at a different node counts, so to capture the dynamic feature of the power behavior. And then the power pattern generally looks like this. So initially it has a significant initialization stage, and later there is an ending part, but the call phase execution basically is the periodic pattern. This one is dense, and if we look at, if we magnify it to just look at the first 500 seconds execution, it's clearly they show the periodic pattern as well. So in the production workloads, these call phase will be much larger than these two ends. So our analysis focused on the call phase execution here. So this is the how the power changes with parallel, the number of nodes and also different benchmarks. So we can see a relatively larger difference between the two benchmarks at the same node count. But if we look at the parallel efficiency, the power usage over the parallel efficiency, the benchmarks difference is almost gone. It's like they are more sensitive to the parallel efficiency. So the power and the performance and the energy consumption on the GPU power capping is shown here. So top two figures show the node normalized performance, and lower part show the normalized total energy. So here, this is a total energy instead of GPU energy. So at 200 GPU power capping, we can check the biggest performance slowdown. We can see this one is about 7%, but the energy saving is about 15%. You can take a look at this larger benchmark. So this is, we submitted this work with much more content than this into a conference. So if you are interested in and send me an email, then I can share the preprint, the manuscript with you. So as a summary, so power capping NVIDIA A100 GPU at 50% of their thermal design power can bring significant energy saving with some performance slowdown. So I don't want to go through this detail, but I have demonstrated with these top applications that there is a big potential. Power capping offers significant potential to reduce operational costs and enhance system throughput. So this part I didn't elaborate, but this is one of the important thing we focus on while we optimize the power usage. Another benefit is enhanced system throughput for future systems. But this is a big benefit of that. And the main message today is you are encouraged to exercise the power capping with your production workloads. So by doing so, you will help the center and the other users as well as yourself when the power is more constrained on our future systems. So we hope we exercise this option and get ready to more power constrained future systems. Before do the demo, I would like to go through the acknowledgement first. So actually, the power capping is root requires root privilege. So in the past, users cannot do it on by end users in the past. But last June, Chris Samuel from our computational systems group, he developed a Slurm plugin so that end users now can do this power capping experiments, apply power capping to their jobs without asking root to help you. So it's quite easy. You just use the Slurm plugin, Slurm directive. It's just the GPU power, SBatch dash GPU power, then provide whatever you want there. So this is a big thanks for Chris Samuel enable this work. The other one is we had a lot of co-authors to enable this work. So for VASP, we listed here, and NERSC and E3SM. And then I also thank the co-authors of NERSC Power Analysis tool that I will demo shortly. So especially I want to point out Fatir Akan and Andy Zhang. They are NERSC's summer intern, and they did excellent jobs during their summer internship here, so that we had this whole understanding of the milk power usage, as well as we have a nice tool to display the jobs power usage. With that, I want to move down to this demo. So this is it's NPAT is the short name for the NERSC Power Analysis tool. So this tool is developed in the it's summer 2023 by Andy Zhang. The URL is here. And this feature has quite a few nice features, but today we're going to focus only the jobs power usage over time view for this tool. I want to show there are some things I want you to know. So data is currently we have data is available for jobs run since April 1st, 2025. So the valid jobs we consider are those like runtime larger than 60 seconds. And this is because if the runtime is too short, then the power measurement may not be accurate as you wish. So we selected the runtime larger than 60 seconds. And we can't do the shared QoS jobs because we measure power per node or its component. For the shared jobs, we can't split between the jobs. So currently, this is the limitation for our power measurement. So if your job run after April 1st, you can find it on this URL. So one thing I want you to know is power usage data from previous day is pre-processed daily for fast access in the web. So if you run job today, you can't see it today, but yesterday's job is available in this tool. So one good feature of this is the power tool is publicly accessible, so no NERSC login is required. And another feature of this tool is the raw usage of data can be downloaded as a CSV format. In general, we don't want people know like what other jobs run, other users run on the system, but we anonymize the users. So for this training, we provide this because if you are non-NERSC user, you might not be able to see you don't have job ID to put in the window of this tool. So we just provided this for once. So you can find available job IDs there, but we remove the username so you don't know who ran that, but you can see their power usage. So now let's go to, for this one, Andy also published this work in one of the SC23 workshops. So you can look at the paper here for more details and more features. Go back. So let's go to this tool. Let me do the demo here. So as I said, this tool has other features. I didn't want to go through in detail for those. And because the code is ready for this website, but the data processing, we had some bottleneck to fix. So I hide those two features in the view. But for this view, this is actually showing the power usage of the Perlmutter system. So I remember someone asked in the QA in the chat if the energy data available, but we don't have total systems. Actually, we do have, but it's not ready yet to make it available. But this is the system's power usage. So basically, you can see Perlmutter uses about 4 megawatt per day. These are corresponding to the maintenance. So the default will show like 1 month, but you can do one as you can put some queries here. You can see even more. Something like this, those are high power usage here. This is interesting one. So those are corresponding to the HPL run when we prepare for the 500, top 500. So this one reach like 6 megawatts per day. power usage over here. But this is just a side talk, and the one I want to show you is here. So this is the another view of this tool. So you can put the job ID here. If you remember any of the job ID, you can put here, and then let me show this. So if you know your job ID, you can put it there and see if it's available. So because it's not easy to, 1 second. Yeah, so we didn't meant to share this with the users, but just for the purpose of this demo, you can, if you like, you can go to here and just randomly pick up some job ID and then try to see if it's available. This is run on 2 days ago. So if your job run longer time, it will take a little bit more time. But in general, this is not sure why this takes longer, but usually within 15 seconds around, you can see like you can display the jobs, power usage over time. So if you want to download the data, you can click this to download it into a CSV file. Then you can see the raw data. So I want to show you here, like for the web display, actually these dots are just, we display 50 dots. So those data will not capture the detail. So if you want to do like even finer grain look, then you can download the data and then you draw the figure by yourself. Perhaps in the future we can improve this display. So if you do like a selection, we may be able to add more data points here. But for now, we can't do that. So the best thing you can do is download the data and then do the display by yourself. So you can see some of the timestamp they missing data. So this is something I talked about earlier about the sampling rate. So actually during the collection time, we do every second, but some of the data just get lost in the data pipeline to the data storage. So we don't have the full data there. But anyway, this is the job display. And we also have, you can also like, you can focus on, for example, if we want to see node data only, you can see this, or you can enable more like this. So you can ignore those GPU utilization, whatever, so it marked, striked out the feature here. So these two developed to have all the features here, but we are missing data. We don't have consistently available data. So we just marked them, like struck them out there. But maybe in the future, we can provide those data as well. So another feature of this tool is if you run like multiple jobs, and you want to download multiple data, then you can use this export tool. So here you can put, another job ID. Yeah, you can put multiple job IDs and then you can download once. Then the result will show up in the CSV file. So I think for the demo, I think that's all. Not this one. Yeah, I think that's all. So if you have any questions, I think you can combine the Charles talk and the mine and also this demo. You can ask questions if you have any. Okay, thank you for your attention.
Thank you so much, Zingji. So if you have any questions, if you could maybe raise your hand using the raise hand button and ask it, or you can enter it into the Q&A doc. And please allow for at least 1 week, 7 business days before we'll reconcile and get all of those answers published and it'll be posted on the event webpage. But we do have somebody, Stayan, if you want to ask your question.
Hi, quick question. Thank you, Zengji and Charles. Very nice talk. So, what's the easiest way to collect the power usage information of the current job? Like, is there an option that we can use in the job script such that when the job completes, we have the power usage data?
I can take that question. So actually, you can do the real-time monitoring while your job is running. But internally at NERSC, we are discussing if we should open up this capability for users. So one way to do that, there are multiple ways, but one easiest way is we have Grafana access to the power data stored in our database. It's called Victoria Metric Database. We can do real-time monitoring. So if you have, let's say, the research need, yeah, just send us an email. I believe we can open that up for individual users, but because scalability consideration as well as the security concerns, so we might not be able to open up generally for all users, but we should support the research need. So let us know if you want to access real time. And another way is we have query scripts that I can share with you. So you can use it, but it's not, we can do almost quasi real-time access for the power data, but yeah, still we need just need to allow you access to our database. The same issue with Grafana. But I think if you write to us, we did enable individual users so far, so I think you should be able to. But for the past jobs, you can use our this web tool. And actually, there are more tools developed to show power and other performance metric. I think the Ruba at our performance group, application performance group, I think his tool will be available soon, one way or another to users. But we are waiting for our NERSC policy update. So if they allow us, we will be able to share the tools with you. Yeah, I hope I answered your question.
Thank you.
Okay.
Do we have any other questions? I see in the chat, Stephen asked a question about information on, I guess, the network or the interconnect availability.
Okay, so let me share my screen to answer that question. So that is a really good question, actually. So I don't know, do you see my screen here? I'm showing the,
Yeah, we see it.
yeah, so basically we don't measure the network's power. We don't have capability to do that. But this node power, it contains the network usage, the NICs usage. So basically you can consider tip of this blue lines, not line, it's stack plot, the tip of the blue part, and you see the white space between the black line, node power, and the sum of the component sum of the the CPU, memory, and the 4 GPUs. These should contain the GPU power. No, sorry, network power. But we don't exactly know how much is for network, but within 10%, that's for sure.
And okay, in the chat, Tapasha asked if there are any studies on power capping on the failure rates of components, I guess.
Well, that is also something we need to look into in the future. But for now, we just did individual application study, not yet at scale. And this is the first time we open up this feature for users. So we may be able to have more data and then investigate that failure rates as well. But in principle, I think other studies shows the reduced failure rate when GPU power capping is applied. At least reduced node failure when power capping applied. That's something I think I read from literature.
Awesome. Did we have other questions? Feel free to go ahead, Nashwan.
So in the third figure, the SI128 underscore, I can see the sudden dips from the 50 seconds to 100 seconds. So, I mean, I just have a curiosity, like why these dips are happening. Like there is no pattern, so there is a sudden dip.
Oh, so this is one of the higher order method. So there are two major components inside the execution. And this is the completion of the first, I think up to here, this is the first phase. And then there are some part of, I believe this is some diagonalization stages involved. Some eigenvalue stuff, I believe. So here they didn't port the code to the GPU. So here basically is the GPU is do the major computation. So the power usage is much lowered. And then after that phase, start another the phase. So that is using GPU. I'm not sure, is this something you are asking?
So my question was basically, so from the user end, like individual users are working based on their CPU requirement or GPU requirement. So I mean, all on a sudden, like, is this the thing? Like everybody stopped working, and then the next work or next job started at some point? Because I mean, like this is so similar. Like so there is a sudden dip, and then everybody started working again, or it just like how this thing's happening, because I'm not sure if I understand this part correctly, because from my end, what I'm understanding is like CPUs and GPUs are used by the users. So all of them probably using it at different times. So there will be like always working. They should be working. That's what I understand. But then if there is a maintenance that I understand, then there will be sudden drop of everything. But I didn't understand that why there is something happening, but not like in full pace or something like this.
Oh, I think you might think I'm showing the system's power usage. It's I'm showing the this specific benchmark during the VASP run. So this is the application behavior instead of system behavior.
Oh, okay. I got it now. Okay, thank
Yeah, so the code contains some
you.
CPU portion, so it has a lower power usage during here. But the other part, I mean, all these patterns basically shows the feature of the application. So they have a implementation doing periodic one. These actually each dip corresponding to a so-called electronic steps inside this computation. They are periodic, iterative. So you can see this type of power behavior. So these are showing applications behavior.
Okay, so these are not individual or systems behavior. It's like application behavior.
Yeah, as a full system. This is what I showed earlier. Like, this is what the system behavior looks like. We can magnify some part of it, this is like a way, this is total system power usage. So we sum up all the, this is actually not the sum up from the nodes. We just directly read the power meter. So this is quite accurate one. So as a system, they have this, down and up and down. And we have another separate study showing that these are the up and down is because the it's just like the job start and start and ends. There are some gap. It's usually depends on the if system runs like large jobs, if large job finishes or if they start, they can have large jump in the total power usage.
Okay, thank you, Zenji.
All right, yeah, thank you. That's nice. Yeah, good questions. Yeah, because I probably should have said that earlier, like this is a power per node when running VASP. This is applications feature. Yeah, it is quite confusing, like if first time, touch this concept. Yeah.
Yeah, thank you, Zengji. Sam also had a question.
Yeah, thanks so much for the presentation. I think this has been asked in the document, but I did just want to ask, just curious, out of how operating conditions work at NERSC. Are there considerations in terms of your local electricity pricing that maybe we wouldn't anticipate? I'm sure you're probably on your own substation and you have, maybe different resource utilization, different availability than residential or commercial sources would have. So are there, just locally, are there particular times at which it would be more advantageous to run jobs? Are there particular fluctuations in pricing where we should try to focus jobs, and then maybe other times where we should try and use more power capping, like in Alameda County?
So as far as I know, I think in the past we did have a couple requests from the electricity provider, say reduce power usage, but it doesn't happen often. And so far, even on Perlmutter, we are not limited by power. So much of the study here is basically we are preparing for the more power constrained future. So if we are really limited by power, then we need to think about, how to reduce. Yeah, that's also one of the strategy. You can do the smart power scheduling so that we can try to minimize the power fluctuations. But so far, the power fluctuations, as you can see here, it's usually are not large. They are about like 2 megawatts. That's it is large, but still we don't get any call from like the electricity provider about the negative impact of this to there, because we are in the Bay Area. I think if for the small town maybe that's more like obvious, but we are small portion of the bigger electricity use of this area. So I think we are fine so far.
So yeah, so you're saying nothing we can do to help with scheduling that would save nurse money, just to practice reducing power usage in general across the board?
I'm sorry, probably I didn't get your questions. So we don't do anything yet for controlling power fluctuations. But if this is but we do have a separate study, even like a charging model. If this is becoming like a bigger issues, then probably electricity providers, they will charge the power by fluctuations. I mean, add some stuff charging for that as well. But in any case, we don't do anything yet with this now. But we do have a study or planned study with a vendor, collaborating with vendors to understand the power fluctuation impact and its solution. we are looking for industry solution for this.
Got it. Thanks so much.
Thank you.
And in the chat, Abhishek asked the question, were there any limitation issues observed from the application side when power capping? Like auto-tuning optimizations because of power limitation. Do you understand that question, Zinji?
Not quite. So maybe from CUDA.
Yeah.
Yes,
Abhishek, if you want to clarify, you're still on.
Sure. Can you hear me?
Yes.
Yes.
All right, great. Sorry, I meant, have you observed any limitations or issues? I meant like seeing incorrect results, or the reason is some of the cuMath libraries like cuBLAS, cuSparse, they have auto-tuning done from a power cap for a specific data type. So if we start limiting power, have you experienced or know any limitations with because these auto-tuning optimizations would change or choose another algorithm because of the power frequency setup, and possibly resulting in some incorrectness, because I'm trying to figure out if we blindly do a power cap, does an application experience incorrectness? Because that's the hardest problem to solve. I mean, the reason could be anything, why you get a wrong answer.
Yeah, I think that's a very deep question for this research actually. So far what we can do is we run application. We didn't expect any malfunction from the from applying power capping. So basically we assumed they generate the same results. It should actually, I didn't carefully check, but that didn't occur to me, like to check the result carefully if we run into any problem. But some code like VASP, definitely it use cuBLAS and these stuff, the math. And I don't know what is the criteria when the underlying the algorithm switches, but that's definitely a real thing. Yeah, I will make a note for this and see what we can do like further to estimate the other side effect from power capping. Yeah, other than performance slowdown. Yeah.
Oh yeah, thank you so much.
Yeah, that's a really good question, because it kind of leads to think that maybe some of the different libraries have to be reprofiled for applications to conform to power capping strategies too. So really interesting question. Okay, well, we are at the hour. Thank you all for attending today's training in NUG Community Call. Thank you to Zingji for the wonderful case studies and demonstration of the tool, and for Lippy for her assistance and help in coordinating and the Q&A as well. Please, if you have not, please take the survey that we have for today available. We value your feedback. And if you have any thoughts or recommendations for future trainings, or if you would like a follow-up on this training, we would love to know and hear from you, as well as any ideas that you have for future trainings as well. Please access the Q&A document. Try to, if you have a question, please try to add as much detail as possible so that we can respond appropriately. So please make sure you review that. If you've asked a question, try to add as much detail as possible. But thank you all for attending today's event. Again, please go ahead and complete our survey for us. And all materials will be posted to the event webpage within 1 week. And an email will go out in the weekly email noting when those materials are available and published as well. So thank you all. Have a wonderful Friday as well as a wonderful Memorial Day weekend.